Okay, Chapter 5, Section 4, Indefinite Integrals and the Net Change Theorem. Okay, in this section, we will continue to develop our understanding of the definite integral and introduce something new called the indefinite integral that is closely related and connected to our ideas of a definite integral. So with that in mind, let's think about the following example. Say we're tasked with finding this definite integral. The integral between 0 to 1 on 1 over 1 plus x squared dx. Okay, so this whole thing. All right, find this definite integral. Hopefully it's clear that the answer to this is going to be some number, right? It's an area. This is not a variable, right? This x here is being used, this function here is being used to establish the heights of approximating rectangles, right? So this is not a variable because the limits are constants. So if we want to visualize what this is an area, right? So let's look at its graph. Okay. Let me go to Desmos. Okay, so here on Desmos, I typed in my equation, 1 over 1 plus x to the power of 2. And we see that this is what the graph looks like. And we're interested in the area between 0 to 1, right? So that would be this shaded area in green. So the integral between 0 to 1 on this function means that it's the area that's above the x-axis underneath a function between 0 and 1. And remember, that interpretation is good as long as this function is positive, which it is in this case. When the function is positive and negative, we have to think of the integral as giving us the net area. Anything below and any portion below the x-axis is considered to be negative. So I'll write that down a little bit, but continuing with this idea. All right, so how do we find this area? At the beginning of this chapter, when we were introduced into this idea of finding areas, we thought about rectangles. So approximating rectangles. Let me use this other website for that. Okay, so in this other website, I typed in the same equation, 1 over 1 plus x squared. And here it is. This is the exact area I want. Using the benefit, one of the features of this website is that it just gives me the answer. So I know that the answer should be right here, 0.786. But we need to figure out how to get that. Okay. All right, so we started off by saying, well, let's approximate it with a rectangle. Let's use the right endpoint, which means that the base of the rectangle, we use the rightmost point to establish its height. So f of 1 establishes this height. Okay, one rectangle. So this yellow one is a good guess for that gray area. Well, as you can see, not a very good guess, but it's an initial guess. And then what do? We add more rectangles to get a better guess. So maybe if we use 2 rectangles, that's a better guess. 3, 4, 5, 6, 7, 8, 9, right? So as we keep going, we see that the more rectangles we use, the better our approximation. Even at 20, we could see that that's a pretty good approximation to the area we were interested in, right? So the exact area there in gray, a good approximation would be to use 20 rectangles, and the computer already tells us what the sum of those 20 rectangles would be at 0.772794, very close to this 0.786. It's a pretty good approximation. If you want it to be better, just use more rectangles, right? How about let's use 30 rectangles. At 30 rectangles at 0.777, oh, okay, even more rectangles. How about at 50 rectangles? At 50 rectangles, 0.7803 compared to the real answer of 0.786, getting very close. Okay, then what we did is we created a formula to do n rectangles, right? The sum of n rectangles. And then we found the limit as n goes to infinity, so we can get the exact answer, no longer an approximation. But that required for that limit to exist. Okay, so let me write that down over here. Going back over here. So early on in chapter 1, to find this answer, option number 1, would be to find a formula that allowed us to add rectangles. So let me write it as 1 over 1 plus x star, let's call it x sub star I squared. And this is where I ranges from 1 to n. And then they have a dx here, right? So the input, right, I'm using a different letter, but just to make it clear, this little input here value is an indexed value from here. And that's where each one of these are sample points, right? We take our domain, we chop it up. So we're going to take our domain from 0 to 1. I'm going to come in here, I'm going to chop it up until we have, let's see, x sub 1, x sub 2, dot, 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 all the way out to x sub n equals that guy. So there will be somewhere in here the ith one. Let's make this x sub I. And then I'm going to make it bigger so I can write down stuff, but they're all supposed to be the same width and a very small width. But I'm just going to draw it bigger so I can write stuff down like that. Each one of these has the same width, and that same width is this delta x, right? So even this one is supposed to have the same width of delta x, where delta x is given by the formula 1 minus 0 over n, or in general, it's b minus a over n, where this guy is the a and this guy is the b. Okay, so this tells me that the x sub star ith value is a sample point from the set that goes from x sub I minus 1 to x sub I. Right? That would be this little guy in here. So somewhere in there, we're going to pick some sample point. Maybe this guy, x sub star I, and that would be a sample point. And then we use that point, f of that point, to establish the height. Well, that's what this is here. Okay, so you can go back and review the previous the first couple of sections in this chapter to look more into this if you wanted to. So we find a formula to do the first n of them. And when we're done with that, when we figure out that formula, then we got to figure out the limit as n goes to infinity, if it exists. Okay, and then that's how we find that area. It's it makes reasonable sense conceptually. It's kind of a hard idea, but we can get there. But it's ugly, right? Very ugly. So it's hard to get very far with this. We need we need to figure out a way to simplify this. Is there a pattern that happens? As these functions themselves get more complicated, then this is going to get more complicated. So we very much needed an alternative way to solve this. This is just ugly, right? Luckily, here comes the fundamental theorem of calculus. So the fundamental theorem of calculus says that if we have some function, say an integral of a function, an integral of a derivative of a function, like this, the integral of a derivative of a function, dx, right? So this is the integrand writing here, all of this, like this. The fundamental theorem of calculus, part 2, says that, well, this is just going to be equal to f of 1 minus f of 0, right? Oh, and well, we introduced a new style of notation to mean this right here. So let me include that as well, since it's important. And usually we like to write this with capitals, so I'll just go ahead and put a capital there, capital F. And so we say it's capital F of x evaluated from 0 to 1. So it's f of 1 minus f of 0. Okay, all right, so this gives us a fantastic, much easier way of solving this integral. All we have to do is think of a way of rewriting this as a function whose derivative equals to this. Right? If this question had been originally given to us this way, like let's say that the original question was given to us in the form of, if the original question had been given to us as the form of find the integral from 0 to 1 of dx, the derivative of 1 over 1 plus x squared, like this, if this had been the original question, then this would be super easy because the integral derivative right next to each other, these undo each other. So all we'd have to do in this case would be to evaluate this guy and say it's going to be equal to 1 over 1 plus x squared, evaluated from 0 to 1. So the answer would be 1 over 1 plus blank squared minus 1 over 1 plus blank squared. And this guy's a 1. Looks kind of weird. 1. And so we evaluate the 1 first, then we evaluate the 0. So we get 1/2, 1 over 2, minus 1. So we get 1/2 minus 1, or negative 1/2, negative 1/2. Okay, well, that would have been nice, but that's not what they gave us. They gave us the integral of this function, not the integral of a derivative of a function. So what we have to do is find a way to rewrite this as a function whose derivative equals to this. And that's what we call antiderivatives. So if we think back to our chapter 3 work with derivatives, recall from chapter 3 that the derivative with respect to x of tan inverse of x is equal to, well, exactly this, 1 plus x squared. So if you remember that, then you know that going backwards, we can restate that guy over there. So the antiderivative, so now going backwards, now the antiderivative of 1 over 1 plus x squared is equal to tangent inverse. I don't like the way that's written. The antiderivative of the function 1 over 1 plus x squared is tangent inverse of x because the derivative with respect to x of tangent inverse of x equals to 1 over 1 plus x squared. Except we have to throw in constants because the derivative of this function equals that, but so is the derivative of that function. And so is the derivative of that function. And so is the derivative of that function. Right? So you can always have an extra constant there and it doesn't affect the derivative. That's why in general we'd say that there would be a plus c that goes there. Okay, so finding the antiderivative gives you this. All right, so thanks to the part 2 of the fundamental theorem of calculus, we have a fantastic, easy, straightforward way of solving this. Let me copy it down here. Okay, so let's start over again. If we're asked to say find the integral between 0 and 1 on 1 over 1 plus x squared dx, right? We'd kind of go over here and think, well, the antiderivative, note the antiderivative of 1 over 1 plus x squared is tangent inverse of x plus c. So that allows me to come over here and say, let me rewrite this 0 to 1, and I'm going to rewrite this as the derivative with respect to x of tangent inverse of x, right? Because I know that this portion here, the derivative of tangent and inverse, is equal to that. And then I can rewrite it like that. And now these two things undo each other, right? So this equals that. And now this, thanks to part 2 of the fundamental theorem of calculus, this is just going to be equal to the tangent inverse function evaluated from 0 to 1 on x, which means that this is just going to be tangent inverse of 1 minus tangent inverse of 0, right? Evaluating at 1, evaluating this at 0. Okay, so if we think about our graph for the tangent inverse function, let's equal tangent. Let's start off with tangent. Tangent looks like this, right? This is tangent of x, and this is the y-axis, this is the x-axis. Okay, so the inverse function is going to look like this. As x grows toward, oh, there's a vertical asymptote here at x equals to pi over 2. And there's a vertical asymptote over here at x equals to negative pi over 2. Right? That's a standard graph for tangent. So that means there's going to be horizontal asymptotes for the inverse function. There's going to be an asymptote at y equals to pi over 2. And an asymptote at y equals to negative pi over 2. And our graph, okay, so here as x approaches to pi over 2 from the left-hand side, as x approaches this way, the outputs go toward infinity. So then the reverse, toward positive infinity. As this goes toward positive infinity, these functions get closer to pi over 2. So it's going to come down like this. And then as x approaches to negative pi over 2, the outputs go toward negative infinity. So then in the inverse function, this is going to look like that. Okay, so we can see that tan inverse of 0 is still going to be 0. And then tan inverse of 1, that's going to be something like this. And we see that that's going to be equal to 45 degrees or pi over 4. Equals to pi over 4. And so that's our answer, pi over 4. Just to get a decimal approximation, we can turn that into a decimal. So just get your calculator and multiply pi divided by 4. And that's equal to 0.785398, something like that. It's approximately 0.785398-ish, something like that. Okay, and so what does this mean? It means that when we were trying to find the area underneath this function between 0 and 1, let's go back to that picture. Okay, remember back in Desmos, we graphed the equation 1 over 1 plus x squared. We're interested in the area between 0 and 1. That's what this integral is, from 0 to 1 on 1 over 1 plus x squared. It's the area between 0 and 1 that's trapped between the x-axis and the function. Remember, that interpretation is good as long as the function is positive. Good. And using technology here, I can just find the answer. I've got to put an x there. And there it is. Right? The computer automatically calculates it, and that's because a is being set as a, let me put a 1 there. There. So that's exactly the same answer we just got. 0.785398, right? This is pi over 4. That's what this is. Okay? So we found that area there. So I think it's pretty interesting that in order to find this region here, this area here, that was our original question, we were able to rewrite it this way, and it just turned into evaluating our function at these 2 points and subtracting them. That's the power of the fundamental theorem of calculus, part 2. It makes it makes a question that would have been really difficult with approximating rectangles a fairly straightforward one. Okay, so that's one connection, that a question about area is turned into a very simple question where we just have to evaluate the antiderivative of that function at the 2 endpoints and subtract them. And so the other important note then is, in order to solve this question, right, we were originally given this question, in order to solve it, we needed to be able to do this highlighted yellow part. We needed to go in reverse here and find the antiderivative. finding antiderivatives is really the most important part of integrals, right? Finding questions about integration, find the integral of this, find the integral of that, find areas, right? Those questions are solved when you can figure out how to rewrite this part of it as a derivative of some function. A lot of that has to do with just knowing your derivatives, but as we move forward, we find that some of the things we want to integrate don't come from very straightforward derivatives, right? It's not just a matter of going back to chapter 3 and reversing all your derivatives. Things get complicated. So there's this whole area of math that's devoted to figuring out antiderivatives, right? Like a little cheat sheet that helps people see patterns so that they know how to find integrals this way, how to find definite integrals. In fact, they've created a new notation for antiderivatives. And that notation is just to put this integral sign without the little numbers. So instead of saying this right here, the antiderivative of 1 over 1 plus x dx is tangent inverse plus c, we note it this way, like this, the same integral sign, except we don't put limits on it, of the function 1 plus 1x squared dx, and that this one is tangent inverse of x plus the constant c. So, the one nice thing, it's both a benefit and a curse here. So it's nice that we have a notation style that's very similar to this one, because that way we establish that they're connected to each other. They're important, they're valuable to each other. On the other hand, it can get really confusing because this is a very different idea than this one, right? When you see little numbers there, this is a definite integral, right? So let's see, this is a definite integral. This is an area under a curve, right? We just saw that's an area under a curve. Whereas this notation here, this is called an indefinite integral. Indefinite integral. And this has nothing to do with areas. This is the reverse of a derivative, the antiderivative. Antiderivative, right? That's its whole goal, its whole purpose for existing is to help you figure out those guys, right? That's the only reason we really deal with antiderivatives, because they become important when you're trying to find definite integrals. And definite integrals are the stuff that makes the world go round, right? We have representative equations that help us in all areas of our economy, of sciences. Lots of stuff involves integrals, and finding those integrals can help us improve profits, decrease waste, and solve any number of problems and issues in our society. Calculus is fundamental to lots of stuff, and all of it involves finding integrals, right? Those equations are representative of something, and finding the integral is representative of something important. So we need to find integrals. To do that, well, we need to find antiderivatives to be able to figure out the answer and take advantage of this of part 2 of the fundamental theorem of calculus. And so for that reason, we need definite integrals. Okay, so there are tables that are created that just have definite integrals, right? Those are like little cheat sheets to help you figure out how to find derivatives. How to find solutions to definite integrals. So for example, you might see a basic table like this one. So here's an example of a table of antiderivatives, also known as a table of indefinite integrals, right? Indefinite integrals, antiderivatives, same thing. And here's a table that has some of the most basic, straightforward antiderivatives. These are really, going back to chapter 3, we learned derivatives, and so from those equations and patterns that we established way back then, we can just come back and rewrite them, right? So for example, the one I just used is right here. So it's, hey, if you forgot your derivatives, here they are in reverse so that we know how to use them. Good. So if you run into an integral that fits this form, I'm trying to integrate a definite integral that involves a b to the x power, then this little thing will help me find the answer, right? So for example, the integral between 1 and 3 on 7 to the x power dx, right? Find this definite integral. Then we come over here and look at our indefinite integral, and it fits this form, b to the x power dx. So using this, I can see that the answer would be b to the x power, okay, that would be 7 to the x power, divided by ln of b, so that would be ln of 7, evaluated from 1 to 3. Good. Remember that when we are applying our definite integral, the constant can be thought of as anything. It doesn't matter. It's going to get subtracted off in a second, right? Because the next step would be to do 7 to the third power divided by ln of 7 minus 7 to the first power divided by ln of 7. And then, you can simplify beyond that. So that would be 7 to the third power minus 7 divided by ln of 7, and, it's good enough. Anyway, point being that this is a great clue to help us figure out how to do that definite integral. Okay, so feel free to use these, these tables that are provided in this chapter to solve our definite integrals. But because we're just learning this, I will warn you that you are limited to just the indefinite integrals that are provided to you in this chapter. So you can't reach out to the internet and find another table of antiderivatives out there that gives you the key to solve some of our integrals. The point of this chapter is to help you develop more antiderivatives. So some of your homework questions will ask you to find these antiderivatives for slightly more complicated cases. So that's part of your work that you need to demonstrate. So you're only allowed to reference the indefinite integrals that are given in this chapter. So let's look at some of the homework questions. Okay, looking at the homework problems in section 5.4, the first few here just ask you to confirm that these antiderivative formulas are correct. So for example, let's take a look at number 2. It says, verify the differentiation by differentiation that the formula is correct. Okay, so all we have to do is confirm that this is true. And remember that the antiderivative of a function f of x dx is equal to capital F of x plus a constant c, if and only if it's true, if the derivative with respect to x on that capital function f of x plus c equals to the f of x. So all we have to do is take the derivative of this function and confirm that it equals that, right? We just have to confirm that the derivative of this function equals that right there. So let's check it. The derivative with respect to x on 1/2 x plus 1/4 sine 2x plus c. We know that its derivative is going to be equal to 1/2 plus 1/4, the derivative sine is going to be cosine 2x. Chain rule says multiply times the derivative of the inside function, which is going to be an extra 2. And the derivative of that guy is just going to be equal to 0. So we have this. Simplifying it, we get 1/2 plus 1/2 cosine 2x. Combining them together, we end up with 1 plus cosine 2x over 2. And from our identities, we know that this is the power reducing formula for cosine. This is equal to cosine squared x. Good. So we've confirmed that, in fact, when you take the derivative of this function, it equals that, right? And so this is an antiderivative, but now its usefulness, it's not part of this question, but why is this useful? So now, if we run into some sort of problem, some sort of a question that asks us to find the integral, and I'm just going to make up some values here from, say, how about from pi over 2 to pi, Find the integral from pi over 2 to pi on cosine squared x dx. We might be asked to find this definite integral. And in order to do that, well, we take advantage of this knowledge right here. This is a function such that the derivative of this function, right, this function exists. This function, if I take the derivative of this function, I get that. So I could rewrite this as the definite integral that starts from pi over 2 to pi on the derivative ddx of 1/2 x plus 1/4 sine 2x. And remember, we get to use any constant, might as well choose the constant 0. So all of this is the integrand and then dx. So I'm just replacing this cosine squared and replacing it by all of that, right? Of course, we skip this step normally, right? We wouldn't bother with this process here. And instead, it's a smoother notation if we just jump right to writing down our function this way. The answer is going to be 1/2 x plus 1/4 sine 2x evaluated from pi over 2 to pi. Good. So all we have to do is evaluate this function at pi minus evaluate this function at pi over 2, and that'll give us our answer. All right, this was going to be 1/2 blank plus 1/4 sine of 2 times blank minus, let me zoom out a little bit, minus 1/2 blank plus 1/4 sine of 2 times blank. So we have to be careful with our signs, so make sure you wrap your function around a bracket so make sure it's clear that it's this whole function exactly written there, including the signs, minus, and then copy that function again. So that this subtraction needs to be distributed. And so first we evaluate this at pi, so we can put a pi there, and a pi here, and then a pi over 2 over here, and a pi over 2 over here. Good. I'm going to erase this here. We don't need it anymore. And then just simplify it as best we can. This is just going to be pi over 2 plus 1/4 sine of 2 pi. Sine of 2 pi is 0. So this whole thing just becomes times 0 minus, and then this becomes pi over 4 minus 1/4 sine of pi, and sine of pi is again 0. So this whole thing is also going to be 0. Gives us pi over 2 minus pi over 4, which just equals to positive pi over 4. Good. So there's our answer. Pi over 4. And we can confirm that with our graphing, one of our graphing tools. Let's go to Desmos. So here I typed in f of x equals to cosine of x squared. I wrapped it in parentheses and raised it to the power of 2. So that gives me this image here. So this is cosine squared. And then I want to find the integral from pi over 2 to pi. So that would be from pi over 2 to pi. Remember, pi is a little bit more than 3.1, right, somewhere around there. So there's pi. And there's pi over 2 to pi. So that would be this green region there. And so from here, you can see that if I just type it into the Desmos graphing tool here, it just gives me the answer, 0.785398, and this is pi over 4. So it gives me that area right in there. Okay, let's do another one. Okay, so then the next few questions ask us to find the indefinite integrals. So for example, let's try number 10. Okay, find the antiderivative or the indefinite integral of this, this function. So the first thing we'd want to do is simplify it. So I'm going to rewrite this. So this means that this is equal to integral from, okay, so that's going to be negative to the positive 1/2 power t squared plus 3t plus 2 dt. Okay, and then I'm going to distribute. So this would be the indefinite integral of t to the 1/2 power t squared plus 3t t to the 1/2 power times that plus 2t to the 1/2 power dt. And then we simplify that. This is the integral as t to the, then we add the exponents. This is going to be 2.5 as a mixed number, or 5/2, plus, this is going to be 1.5 as a mixed number, so that'd be 3 times t to the 3/2, plus 2t to the 1/2 power dt. Right, so this is a dt, applies to all of it. Okay, so now we can just use our pattern that we established with antiderivatives using the power rule. We know that when we take the derivative of a function, we subtract 1. So now if we want to find the antiderivative, if we want to go backwards, we're going to have to add 1 to the exponent. So I'm going to go through and copy this guy and just add 1 to it, plus 1. But of course, that means that I need a common denominator, so let's write it as a 2/2, which is going to bring me to 7/2. Okay, so this is going to have something to do with a t to the power of 7/2. I know that when I take the derivative, I'll bring that 7/2 down and subtract 1. That'll give me the proper exponent, but then I don't want that 7/2, right? So we fix it by using the pattern that whatever that number goes, that whatever number you put there is a value that goes underneath a fraction here. So this is going to be 7/2, like this, which, okay, over here would have been 1/5/2 plus 1, which is that same exponent. Okay, so we follow that same pattern for the other two. This is going to be a 3 out here. I'm going to skip a step there, and this will be t to the power of 3/2 plus 1. So I'm just going to put a plus 2/2. And that's going to get me to 5/2. This will be 1 over, and then this will be 3/2 plus 2/2 in the denominator. So down here, this would be 3 times, and then this becomes 5/2. So it'll be t to the power of 5 divided by 2. And this becomes 1/5 divided by 2. Plus, and then likewise for the last one, 2 times, make space there, t to the power of 1/2 plus 2/2. Plus 2/2 gets me 3/2. So this will be 1/1/2 plus 2/2. So this will be 2 times 1 over, and then t to the power of 3/2. So we put a little 3/2 here. Let me zoom out. Okay, so then simplifying this by multiplying the numerator times the reciprocal of the denominator, we can flip this upside down and say that this is 2/7 times t to the 7/2 power plus 3 times 2/5 times t to the 5/2 power plus 2 times 2/3 t to the 3/2 power. And at this point, you might notice there's a very nice pattern. You know, these two middle steps you could probably skip, and so it's perfectly reasonable to go from there to there with a little bit of practice, right? So these are very often skipped steps, which is perfectly okay, right? Whatever makes sense to you. Okay, so then maybe just multiplying those guys there, we almost get to our answer. It'll be 2/7 t to the 7/2 plus 6 over 5 times t to the 5 over 2 plus 4/3 t to the 3 over 2. And don't forget that plus c, constant, right? Any constant. And that's it. That's our answer. So let me just copy the original one back down here. This is the integral, indefinite integral of root t squared plus 3t plus 2 dt. dt is equal to this. And then on the left-hand side, I was supposed to copy them all the way down. So I'll just put that on the left-hand side. They're all the same. Same over here. Okay, and so what we've established is this nice little rule. So if someone needs to solve definite integrals, maybe they have a bunch of definite integrals that all fit this pattern, we've helped them establish a nice little rule for it, right? So this isn't part of the question, but, why is this useful? Well, now, let's say someone has to solve this question. What is the integral from, put 0? Yeah, let's say 0 to 1 on the square root of t squared plus 3t plus 2 dt. They want to solve this. Well, we have a formula for them. It's right here. This is the antiderivative, so we can just jump right to it and go, okay, well, all you have to do is evaluate this t to the 7 over 2 power plus 6/5 t to the 5 over 2 power plus 4/3 t to the 3 over 2 power. Evaluate that from 0 to 1, and that'll give you your answer, right? So we've made a formula that helps people solve this integral if they run into it, this definite integral if they run into it. Good. So the ones that are common, the ones we run into very often, make it onto these tables so that you can look it up. So if this is an equation that happened to appear a lot for some reason, maybe this has to do with our electrical power grid and we need to integrate something so we can figure out wattage and, or maybe it's an equation that appears in rocket science a lot and it has something to do with nozzle velocity and strength and I don't know, it could be something. So if this equation appears a lot, then in order to have like an easy button to integrate, this formula that we just created might make itself onto a table somewhere. So people don't have to repeat these steps so often. They can just go right into our formula, right? That's the whole point of indefinite integrals, to make it easy. It's an easy button for finding definite integrals that have the same pattern. Okay, let's do another one. Okay, so now let's try some of these definite integrals. So how about something like number 27? Okay, so find the definite integral from 0 to pi on 5 e to the x plus 3 sine x dx. Okay, so this should be a really easy one. We're going to say that this is equivalent to, well, we know one of our properties of definite integrals, we can separate into two separate integrals. So this is going to be equal to the integral from 0 to pi on 5 e to the x dx plus the integral from 0 to pi on 3 sine x dx. Next, we know we can pull out a constant, so this is equal to 5 times whatever is the integral from 0 to pi on e to the x dx plus 3 times the integral from 0 to pi on sine x dx. Good. And then using our very simple derivatives, we know that the derivative of e to the x is e to the x, therefore the antiderivative is just going to be e to the x. So this is just going to be equal to 5 times, and this is going to be e to the x evaluated from 0 to pi, plus 3 times, and now the derivative of sine is going to be cosine, so going backwards, the derivative of cosine is almost sine. We just have to be careful with an extra sign. This is negative cosine of x. evaluated from 0 to pi, right? So this is kind of a guess and check. The derivative of e to the x is e to the x, and the derivative of cosine x is negative sign, so I have to throw in an extra minus sign to make it a positive sine x. Okay, so then we can simplify this a little bit. I could have just kind of skipped this middle step and brought them together like this. So this could be 5e to the x minus 3 cosine x. And since they're both being evaluated from 0 to pi, I can just kind of tuck it under one big thing like this. So here, this bar here is applying to this function because we were finding the result of this integral, whereas here, this value here referred to this one because it was the result of that integral, definite integral. But we can just kind of tuck them all under one big happy one and say all of this applies to this. Okay, so now what we have to do is evaluate this very carefully. This is 5e to the power of blank minus 3 cosine of blank minus 5e to the power of blank minus 3 cosine of blank. And be real careful with your signs. So let's wrap it around parentheses. So it's this one, like this, with a minus. I'm going to evaluate pi in there, minus this one. Again, evaluate it very carefully. Include the pi, the minus. So for the first one, we're going to evaluate this at pi, e to the pi, cosine of pi. And then for the next one, we're going to evaluate this at 0. So e to the 0, cosine of 0. Okay, so simplifying as best we can, this is 5e to the pi. That's fun. Cosine of pi is equal to -1. So this is -3 times -1. Cosine of pi is -1. Minus e to the 0 is 1. So this is just going to be -5. Plus 3 times, and then cosine of 0 is equal to +1 times 1. Good. So minus makes it a +3. We have another +3. Minus 5. So this becomes 5e to the pi. +3 makes it +6. Minus 5 makes it +1. And so as an exact solution, that's as good as it gets. So I'm just going to copy our definite integral one more time. Integral from 0 to pi on 5e to the x plus 3 sine x dx equals to this number. Let me box it up and zoom out. And then on the left-hand side of this equal sign, it's the same definite integral getting copied all over again. So I'm just going to say on the left-hand side, all of this is supposed to be the same. So using our calculator, I can approximate this to be approximately equal to 116.7034, approximately. And then we can use technology to approximate this, or to confirm that this work is true. Okay, so to confirm our work, we can use technology. Let's come back to Desmos and confirm that that really is the answer. So our equation is going to be, let's type this away, this is going to be 5e to the power of x plus 3 sine x. So here's our function. Let's get rid of this thing. Here's our function. Let me zoom out a little bit more. So it blows up quite quickly. And we're interested in integrating between 0 and pi. So let's go from 0, and that's the same answer. So 116.03, that's approximately the same answer we were getting over here. 116.7034. Okay, so we're getting the same consistent answer. And then we can visualize here by graphing this from, or highlighting the area between 0 and pi, which is that little area right there. So let me zoom into it, and let's come over here and change this settings. So let's make the x-axis go from, remember, pi is 3.10, so it's really close to 3. So let's say from -1 to 4. So if we just zoom from -1, from -1 to 4, if we just zoom into that part of it, it just looks like this. So it almost looks like it looks a lot like just e to the x or something. But of course, if we zoom into here, we see that something weird is happening where this goes down and up and up and down. So you got to be careful with your settings. Your graph might lie to you. Anyway, so we find that this area in green here, from 0 to pi, on this function equals to 116.703. Okay, so it matches up with our work that we did over here. All right, let's try one last one. All right, let's do one last one from this section, and let's do one that involves absolute values. So let's explore that idea. Let me do number 46. Okay, so find the integral between 0 and 3 pi over 2 of the absolute value of sine x dx. Okay, remember that when f of x is positive, so if f of x is strictly greater than 0, then when we find the integral from a to b on f of x dx, oh, of course, f of x also has to be continuous. F of x continuous on the set from a to b. Okay, so when f of x is positive, we can visualize this as the area underneath the function. So we often do this. Let's say this is f of x. And then we go, okay, from a to b, like that. And so we're talking about the area that extends from here to here. So we like to think of it as the area, this definite integral, we like to think of it as the area highlighted in yellow, right? The area underneath the function. Okay, but if we remove this little thing here, if we don't necessarily say that it's always positive, it's allowed to be a function that's above the x-axis, a function that sometimes is above the x-axis, a function that's sometimes below the x-axis, then the integral takes on a slightly different interpretation. So if that's the case, then it might look more like this. The integral from a to b on f of x dx is equal to, let's say that the function looks like this. It sometimes goes above the x-axis. Oops. It goes up and then down and then up and then down. Let's say it looks like this on the interval between a and b, like that. So the function still has to be continuous. But now we're going to have 3 different areas to think about. So there's going to be area 1, which is maybe this yellow part. Area 2, let's say that's this little yellow part. And then there's this blue part, which is area 3. Because the function goes below the x-axis, right? Okay, a couple more labels here. This is the y-axis, this is the x-axis, and we're saying that this is some function f of x here, where f of x goes above the x-axis, goes below. Okay, so any area below the x-axis is counted as a negative. So when we find the integral, it will automatically give me the total net area. This answer will automatically give me a sub 1 plus a sub 2 because they're positive, and automatically subtract the area of a sub 3. Okay, that's automatically done. That's what the integral does. Remember that one way to thinking about this is to approximate it with rectangles. And if we use the function to estimate the height of the rectangle. So if the function is negative, then those rectangles are going to be negative answers as well, right? When we insert approximating rectangles over here, when we insert approximating rectangles over here, they're going to be positive values. But when we insert approximating rectangles over here, well, the height's going to be negative, so it's going to give us negative values, right? So the integral automatically does this for us. So it's useful to think of it when f of x is positive as the area underneath the function, but it's really equal to the net area where positive areas above the x-axis are subtracted from the areas below the x-axis. Okay, so what would we have to do if instead of asking us this question, they asked us to find the absolute value of this question? So if we had to do this, what's the absolute value from a of b of the absolute value of f of x dx? Well, what we have to do is figure out what portions are below the x-axis so that we can break this up. So let's say that this value here is the value, the letter k, and this one is the letter w. So we're going to have to break this up into 3 separate integrals, where 2 of those integrals are going to be positive. So to go the integral from a to k on f of x, I don't have to worry about making it absolute values because I know it's positive in that zone, dx, plus, and then this one, which would be the integral from the letter w to the letter b on f of x dx, plus, and now I have to be careful because when I do this integral, the integral from k to w on f of x dx, I know this is going to give me a negative answer. So I have to multiply it by a -1 times -1. That'll guarantee that it's positive. Good. So then this will give me area 1, plus this will give me the area 2, and those are all positive, plus, and then I'll have this -1, and then this is going to give me area 3, and it's going to guarantee that I get a positive answer, right? So this answer right here, this will be a sub 3, and a sub 3 will be a negative number, so that's why I multiply it by this -1, thereby guaranteeing that I get all of the area, not the net area, which is what this wants, right? If I make the absolute value, if I consider the absolute value of f of x, that would mean that this function gets brought up like this, like a reflection about the x-axis like that, and so we'd have this, right? We'd have to move this up here. Okay, so now back to our question. We were dealing with sine. So back to us, we were dealing with the sine of x function. Let's look at the graph of sine of x. Okay, so coming back to Desmos, I can change this function back to sine of x. And let's change our parameters here. Let's go from -2 pi to +2 pi. And let's go from -1.5 to +1.5. There it is. Okay, so here's our sine function as we know it. Maybe I should zoom out. Here's our sine function. Okay, and so we could be interested in the area trapped between 0 to pi. That would be that green zone right in there. Let's zoom in. From 0 to pi. Or I can go from 0 to pi over 2. Oh, I have to change this. 0 to pi over 2. And so it'd be kind of half that right there. Good. Okay, or I can make this a variable. Let's make this a moving variable. And let's make it a. And let's make this guy a. So now as I move this variable, we can see how the area changes. Okay, so for the section between 0 and pi, for this zone, the sine function is just positive. So again, we can continue to interpret it as the area underneath the function, for that zone at least, and it just becomes that. But as soon as we let a go past pi, then we reach the negative territory. And so this is considered as a negative area, and it's going to subtract away from that. Right, so let's take a look at this right here, which gives us the total area. Notice that when we're over here, start off at 0, right? And then as we let a get bigger and bigger and bigger, that green gets bigger and bigger, we trap more and more area. It's getting bigger and bigger and bigger. Even though the function begins to go down now, we're still adding area to it, just maybe not as much, but it's slowing down, but we're still adding area. So this number just keeps getting bigger and bigger and bigger and bigger until we get to pi. Well, this is not going to let me get right to it, but right when we get to pi, it'll stop growing, and then it'll start getting a little bit smaller as we go into the deeper into the reds, right? Until we get to a point where they kind of cancel each other out, and right around there, the answer is almost 0, right? I can't get the exact number, but it's pretty close to 0. At this point, the green and the red kind of cancel each other out, right? So the integral from 0 to 2 pi is just going to be 0. They cancel each other out. Okay, but what if I just wanted the absolute value of this function, meaning that I want to put this red one above, flip it upside down. I want both of these areas where this is also considered to be positive. Well, I can graphically see that this is just going to be the answer from 0 to pi. The integral from 0 to pi on sine x is just going to be 2. And this should be the same result when we go down here. From pi to 2 pi, we should get negative 2. So if I want to make this positive, I know that the answer is going to be positive 4. Right? So pictorially, I already have my answer if I want to go from 0 to 2 pi. Good. Now, having technology makes it easy to figure out the answer by just simply using the absolute value function. So let me go right in here and say that this is going to be reaching in here. There's an absolute value function like this. And then in here, we're going to type in f of x. Close the absolute value function. And then we get that. So, the computer automatically calculates the answer for us, that the answer should be 4, where 2 units come from this green one, and then 2 units come from this red one. We add them together, keep forcing this to be positive, and the answer is 4. Okay, but for our particular question, they asked us about 0 to 3 pi over 2. So let's put that over here. 0 to 3 pi divided by 2. 0 to 3 pi over 2. Okay, so let me highlight the region of interest. So this goes from 0, and this goes up to 3 pi over 2. 3 pi divided by 2. Up to there. Okay, so from the picture I see that I'm going to have to break up this integral into 2 parts. The hard part when you're dealing with absolute value functions is that you have to manually figure out when does your function begin to go below the x-axis, so that you can break the integral up into more than one integral, sometimes 2 or 3 or more, and manually calculate it so that at the answer, the result turns out to be positive. Okay, all right, so let me copy this down. Okay, so this is the sine function. So let's say this is the sine of x function. So this is the x-axis, this is the y-axis going that way. Okay, and so we can see that from this point to this point, which is pi, this function is above the x-axis, so I know that this area in green is going to be positive. Let's call that a sub 1, and it's going to be positive. And I know that this area, when I integrate it, it's going to give me a negative answer, a sub 2. So if I was just asked to integrate from 0 to 3 pi over 2, 3 pi divided by 2, on sine x dx, I know that the answer would be capital A sub 1, which would be a positive number, plus this negative number, negative A sub 2, or just subtract them off. Visually, I can already see that it's going to end up being half of this. And we already knew from earlier, just using the technology, I already knew that this answer was going to be 2. This whole area is 2. And I can already see from this that it's going to be an answer of negative 1 down here. So I can already tell that this is going to be equal to 2 plus negative 1. So the whole answer is just going to be positive 1. That's this integral. But I don't want that. I want the absolute value. So I want my answer to be positive 3. I want to make sure that this is positive. I want to take the whole area, regardless of whether it's above or below the x-axis. The absolute value forces the sine function to always be positive. So when I apply the absolute sign to the sine function, it turns my sine function this way. It's going to come down to here, and then instead of going down to the negatives, it comes up like this. Well, that's ugly, but you get the idea. It'll make it go like that. And so this area comes this way, like this, and so this is the area I want, right? It forces the sine function to be positive. Okay, so armed with all that knowledge, this is what we have to do. We have to take this integral and rewrite it as the integral from 0 to pi on sine x. We don't really do anything there because from 0 to pi, sine x is already positive, so the absolute value is not doing anything. Plus, and then separate that into the integral starting from pi all the way out to 3 pi over 2 on sine x dx. I know that this will automatically give me a negative answer. I already know the answer is negative 1. But I don't want it to be negative, so that's why we have to introduce this times negative 1 here to force it to be positive. Okay, and that's the tricky part. And that's how you get rid of the absolute values, right? That's how we dealt with it. This used to have an absolute value here, absolute value there, absolute value there. Don't ignore it. And the way we deal with it is figure out when is the function positive. Okay, it's positive here, so we don't have to do anything. And when is it negative? Oh, it's negative in this part of the graph. So that's where we throw in this extra minus 1. Okay, all right, so now we just simplify this. This is going to be equal to negative 1 times cosine x. The derivative of negative cosine x is positive sine x. So this gets evaluated from 0 to pi plus, and I'll leave this negative 1 in red to see where it comes from. And then this has its own minus 1 times cosine x. And this gets evaluated from pi to 3 pi over 2. Okay, so now very carefully evaluating this, we get minus 1 times, and then it'll be cosine of pi minus cosine of 0. Plus, and now negative times the negative makes it a positive, so these two kind of cancel each other out. So I'll just have a plus sign, plus, and it'll be cosine of 3 pi over 2 minus cosine of pi. Okay, cosine of 0 is equal to 1. Cosine of 0 equals to positive 1. Cosine of pi is equal to negative 1. Cosine of pi is equal to negative 1. And cosine of 3 pi over 2, that's cosine of pi and a half, that's equal to 0. So let's be careful with all these. This is equal to negative 1 times, and this is negative 1 minus 1, plus, and then this is going to be 0 minus negative 1. Okay, let me zoom out a little bit more. So now this becomes negative 1 times negative 2, which gives me positive 2. That confirms what I thought. This 2 is this answer. So we found the area of the green. The area of the green is 2 units, confirmed by this, plus, and now this turns into negative, negative, just becomes 1. And so now we've confirmed this part. The area of this one, well, it used to be negative 1, but now if we think about it in its absolute terms, then the area of this up here becomes 1. This area here is 1 unit. So the whole summation is going to be positive 3, just like we wanted, equals to 3. So we had, this guy, the integral from 0 to 3 pi over 2 of sine x dx equals to positive 1, because we get 2 plus negative 1 gives you positive 1. On the other hand, the integral from 0 to 3 pi over 2 of sine x dx, and then in absolute values here, absolute value, we see that this one is just equal to positive 3. Right? And that's the answer they wanted. This is the one we're working with. Okay, so all the questions that have an absolute value are, a little tricky. You really have to think about the graph, think about when that function is below the x-axis, when it's above the x-axis. So you might have to set up that equation, whatever that integrand is, whatever that function is, set it equal to 0, solve, figure out when does it equal to 0. And then think about your limits of integration to see which portion of that your function will be above the x-axis and what portion of that it'll be below the x-axis. Okay? Anything that's below the x-axis, you're going to have to introduce this extra minus 1 to guarantee that it's positive. Okay, so hopefully that should be enough to tackle your homework from this section. Please let me know if you have any questions.